I'm going to start just sharing the Emacs window and not everything else, because I just want to start by talking about the new types. So we're going to start over here. So I don't know if you guys remember exactly what was here before, but we're going to add a new type of statement. So before we had let, today we're going to add let rec. So recursive let that lets you define functions that refer to themselves. Similarly, we're going to add let and let rec expressions. We're going to add function expressions, also known as lambdas, but the keyword in PicoML is fun instead of a backslash. We're going to add application expressions, so that lets you actually call functions. And then we're going to add what are called monadic operators and binary operators. Monadic is a confusing term because they're not related to monads in any way. It's just another way of saying unary operator that for some reason people like. But yeah, so we have monops and binops. And then the rest of this was here already. So constant expressions, variable expressions, if expressions, we have all of that stuff already. For the monops and binops, though, we also need a data type that describes the operators themselves. So our monadic operators, we have integer negation and Boolean not. And for our binary operators, we have integer addition, subtraction, multiplication, division, floating point versions of all of those things, comparisons, so equality, less than, greater than, etc. We have Boolean and an OR. These do have short circuit semantics, but as I've spoken about before, because of Haskell's laziness, we basically don't have to worry about that. We get it for free. PicoML at this point still doesn't have side effects. You can't mutate any variables or like print things or anything. So short circuiting doesn't really mean anything anyway. We have another operator called cons, which is list cons. So in Haskell, that's the single colon for prepending ahead onto the tail of a list. In PicoML, it's a double colon, but it does the same thing. And then we have the string concatenation operator, which is the caret. So what you would probably be used to is exponentiation. That's just what ML uses. And that does exactly what you'd expect. It concatenates two strings. So that's all the new types. Personally, I think most of the interesting stuff is the typing rules and the evaluation rules. I don't think the parsing is all that interesting, but I do want to talk about it. So if we just come over here, you can see there's a bunch of new stuff added to this language definition that wasn't here before. So we have this arrow. This is part of the lambda syntax. We have all of these math operators. The ones with dots after them are the floating point versions. The ones without dots are the integer versions. We have all of the comparison operators. The equality comparison is not double equals, it's just single equals. So we use the same operator that we were using before. Double colon is cons, and an OR, and then string concatenation. And then there's also a few new reserved words. So fun and rec. So when we write let rec, we don't write one word, we write it with a space. So let space rec. Yeah, nothing new here. Let me get rid of that highlighting, that's annoying. So the first major change is because we have let expressions, but we also have let statements, we run into this thing called a common prefix problem. If the first thing you see when you start parsing a statement is the word let, you don't know until all the way after you're done with the body of the binding, and you see either a double semicolon or the keyword in. You don't know if you're looking at an anonymous let expression or if you're looking at a let statement. And so I rewrote the entire let statement thing to distinguish that automatically. And so now there's two different ways that you can parse a let expression. One of them is through parseExp, but the other one is through parse let statement. There are other ways to solve this problem. This was the most direct. This is one of the major reasons that you would use a parser generator instead of combinator parsing once you start adding more complicated language features like this. It's because for a parser generator, this is no problem at all. It will figure out how to build a parser despite common prefixes, despite all sorts of other things that cause problems for combinator parsers. But here we have to figure out how to solve them ourselves. So in this case, it's mostly what it was before, except after seeing the reserved word let, we also check if there's the reserved word rec. If there is, there's going to be an additional identifier because you're not allowed to make a recursive binding for a value, only for functions. So for example, you can't say let rec x equals 5 because that would allow you to write let rec x equals x, and now you have a problem, right? That term will type check, but it's useless because it will always cause an infinite loop. So we just disallow it entirely. So yeah, if we see the reserved word rec, there's going to be 2 identifiers, otherwise there's only 1. Then we look for an equal sign, we look for the body of the binding, and then we check, maybe we're looking at an expression and not a statement, and then there's going to be the keyword in, followed by another expression. And then depending on which of those things we had, maybe the keyword rec, then we have recursive bindings. So that's the just cases of both of these. This one's let rec statement, this one's let rec in expression. And then also whether or not we're looking at a statement. So if there's something here, like if this is, sorry, if there's nothing here, if this is nothing, then we're looking at a statement, right? There was no in keyword at the end. If there is something here, then there was an in keyword at the end, and we're actually looking at an expression. And so we need to return an anonymous statement instead of a let statement or let rec in statement. I think this is actually the most complicated part of parsing this stuff, but it is pretty annoying, and sometimes it can be really hard to get right. I wouldn't be surprised if I did something wrong. It happens. The other thing that I did is I started adding these angle bracketed question marks. This is a feature from Parsec that gives better error messages. So if it's trying to parse an expression and none of these cases match, if you don't include the bracketed question mark, then it will produce an error that says like unexpected whatever character it saw, expecting either a reserved word if, fun, let, and then it will also include all of the things that an operator expression could start with, which is a lot of things, because an operator expression can start with any expression, which could start with a variable name, a constant, which could be, you know, a number, unit, a string, etc. So this would give you a huge message. So instead, this just overrides the error message, and it says unexpected token, expected expression, which is much nicer. And also what you'd expect to see from a language. That's not necessary, but it's a nice feature. But now here is where most of the new work for this week happens. Parsing operator expressions is really hard because you have to deal with precedence, you have to deal with associativity. So for example, if someone writes 1 plus 2 times 3, it's really important that you parenthesize that as 1 plus quantity 2 times 3 and not the other way around. And also, if someone writes 1 plus 2 times 3, you need to choose if you're going to do 1 plus 2 first or 2 plus 3 first. And so the first thing is called precedence, the second thing is called associativity. In our case, you can see plus here associates left, so we would choose to do the 1 plus 2 first because it's on the left. And then also, this is just, this doubly nested list is a whole precedence table, hence the name table. And so things that are higher up have higher precedence. So because this list containing all the multiplication and division operators is higher than this list, which contains addition and subtraction operators, the multiplication and division operators will bind tighter, which is what we want. But then things in the same list don't bind tighter than each other. So if you write like 5 times 3 divided by 2 times 4, you'll just get the whole thing associated to the left. So 5 times 3 first, then divide by 2, then times 4. And that's because all of these operators together associate left. If some of them associated left and some of them associated right, well, you might think, well, then how do you decide what parentheses to place where? And Parsec actually agrees with you. So if you do that and then you try and parse an expression like 5 times 3 divided by 2, whatever, you get some nasty error that says can't mix left associative times with right associative divide or something like that, I think. So yeah, we don't want to run into that at all. We want everything to be left associative anyway, so we just leave all of these left associative. Okay, so then we get to operators like this. So this is a cons operator. This is the one that makes lists. Remember that lists are linked. So as you go from left to right, you're including, so for example, actually, it's easy to talk about, but easier to just show an example. say you write an expression like this, right? Each one of these things is a list element. But the thing at the end is a list, right? So cons is not symmetric. It takes an element on the left and a list on the right. So over here, when we're looking at this cons operator, we need the thing to the right to be a list. And so that means we want to evaluate this first, because this will return the list containing only 3. And then we want to evaluate this operator. So put 2 on front of that list, etc. So we actually want this one to associate to the right. If we make it associate to the left, it's wrong. And that would lead to some very confusing type errors for unsuspecting users. So we got to make sure we get that one right. String concatenation doesn't matter so much. Making it associate right is more efficient for implementations of strings that are backed by linked lists, which in our case it is because we're using Haskell strings. In a really efficient implementation of a language, though, it shouldn't matter because your strings are probably backed by array lists, and then it doesn't make a difference. Comparison operators associate left by choice, but it doesn't really matter because putting a bunch of comparison operators in sequence is probably not well typed anyway. And then for and or, it's important that these associate right because of short-circuiting semantics. I mentioned earlier that because our language doesn't have any side effects right now, the short-circuiting semantics don't really mean anything. That's still true, but we still want to get it right, because say we were to add side effects later, like printing things to the screen, we still want to make sure that the short-circuiting semantics work correctly without having to be changed. So just get it right off the bat, make sure they associate to the right. These are a few helper functions that help put the table together. If you're interested in how this works, you can look at the parsec documentation for this build expression parser function. This is the function that's really doing all the work. I could talk about this function for a long time. It's very interesting. How it works is pretty cool. But the documentation for it is really good anyway. So if you're interested in that, you can go check that out. But essentially, it just builds a parser that handles all of the issues with precedence and associativity for you. Then we come to the things that that can go on either side of the operators. So the things that aren't themselves operator expressions, but are the terms. So we call these AEXPs. We're not using A as the article. It's short for application. So this means application expression. And the reason that parsing these is kind of tricky is because if you think about the context-free grammar rule for this, it would really look, something like this, right? An AEXP is either an AEXP followed by an atomic exp, or oh, I didn't put a comment at the front of the line. Yeah, no, go back. There we go. Or an atomic exp, right? So for those of you that have seen context-free grammars before, hopefully this makes sense. The problem is AEXP is what's called left recursive. The first string in it, the first symbol in its production string is itself. And so that means if we were to just try and do this normally with our recursive descent parser, we would have parse AEXP equals parse AEXP followed by stuff. That's going to cause an infinite loop, right? You can never actually make any progress. So parsec has a function for dealing with that too, called chain L1. And what it does is it recognizes that whenever you have left recursion like this, you're trying to build a list, right? In this case, we want a list of atomic expressions. But we're trying to build the list so that it associates to the left. That's why we're using left recursion. So chain L1 just parses a list of atomic expressions, but then you also have to give it a function to combine the individual atomic expressions with. So in this case, we use appexp. So this makes us parse a list of atomic expressions and then fold them through appexp. So we end up with a kind of tree of application expressions. If you'll notice, what that means is that when you write the application, say fxy, f applied to x applied to y, you're not applying the function f to 2 arguments. What you're doing is you're applying the function f to 1 argument, and you're getting back a function which you're then applying to another argument. Right. So that's the same way it works in Haskell. That's called currying. And it's not necessarily immediately evident from the evaluation rules that that's going on. But you'll see that it works and it's very natural. And in Haskell, it makes a lot of sense to write things like that, because that's what lets you, for example, use the map function over lists easily, because you can partially apply the function that you're passing to map, give it, say, maybe 1 out of 2 of its arguments, and then the rest of the arguments come from the list that you're mapping over, just for example. And then again, more of these bracketed question marks. What's an atomic expression? An atomic expression is anything that can go like at the base, any single constant, easily evaluatable expression, not necessarily constant, as you'll see, but the important thing is just that it goes at the base level. So how that works is we either have a constant or we have a variable, right? Those are the simple expressions. Or we have a complicated expression, but it's surrounded by parentheses, right? The parentheses tell us how to, like explicitly how to associate the expression, because parentheses make association explicit. And so that means when there are parentheses, we can just treat it like a base expression because we already know the extent. Lists are similar because the thing is surrounded by brackets, so we know the extent. There is one complication, which is again a common prefix problem. This parens case and the unit expression both start with parentheses. So we have to deal with the fact that we might start trying to parse a unit constant and then see that the next token is not a closed parenthesis. And so this try Combinator just lets us backtrack quickly. Normally you want to avoid this because if you use backtracking too much, you can get exponential explosion. But in this case, we're always going to backtrack after exactly one character if this is going to fail, so it's fine. Right? There's no chance for any really bad behavior here because we're going to backtrack before we could make any other decisions that we also need to backtrack. So this is fine. And then I don't think anything else here should have changed. So the only other major changes are, if I go back up here to this parse x function, you can see we've added a couple of cases. So there's parse fun, parse let, parse opx we talked about. That was this operator table. So going back down here to parse a function, we look for the keyword fun, an identifier name, that's going to be the argument, the arrow, and then the body of the function. And then for let, we do basically the same thing that we did for the statement, except now we don't have to worry about the fact that it might be anonymous because we know we're parsing an expression. Other than that, it looks exactly the same. So it's just this last part here at the end isn't optional anymore. Here it's required, but other than that, it's the same. And yeah, that's the whole parser. There is one other thing I added. So last week we could only parse empty lists. This week, now that we have operators, we're parsing lists using what's called the desugaring method. So instead of producing a list expression that contains a bunch of other expressions that we need to evaluate in sequence, instead we just replace a syntactic list with the equivalent expression using cons. So for example, if the user writes 1, 2, 3, and lists are separated by semicolons in OCaml, then we replace this with 1, cons 2, cons 3, cons nil. And then we'll just evaluate this expression instead, since they're supposed to be totally equivalent. And we'll type check it this way as well. So yeah. This uses a different combinator called sepby. This is kind of like chainl, except in this case, we don't need to solve any kind of recursion rules. We just want a list of things. Previously, we've used many for that. Like over here, we used many1 to parse a non-zero number of digits. The only difference is that sepby also lets you give it a separator. So in this case, I want them to be separated by semicolons. There's a similar combinator called sepby1, which also requires that there's at least one thing there. But in this case, we're okay with empty lists, right? So we don't need that. So okay, then we get to type checking. This is the part where we want to really start talking about the new rules. As you can see, we're going to have to add a whole bunch of stuff here. But before we can do that, I want to show you the rules as well as one new helper function that we need to implement the rules. So I'm going to stop sharing my screen and then start sharing my whole screen instead of just Emacs. Okay, can you guys see the typing rules on the side?
Yeah.
Yep.
Okay, good. Oops, that was not far enough. Yeah, there we go. Okay. So just before I start talking about the typing rules themselves, I want to talk about a couple of new things over here because we're going to need them very shortly. So first of all, we still have this signature function for getting the type signature of a constant. And you'll see still the only interesting type signature is nil. But But we also have these new functions for getting the signatures of monadic operators and signatures of binary operators. This function looks scary just because there's a lot of cases, but the things, the guards, the things to the right of the vertical bars, these are just picking which case we have. It's the things to the right of the arrows that are actually producing results, and these are all very simple, right? These are just make a binary operator that takes 2 integers and returns an integer, make a binary operator that takes 2 floats and returns a float, etc. And then all the types are really defined down here. So we have this function for just making a binary operator that takes 2 arguments of the same type and returns some result. We have the type of comparison operators. Comparison operators for us don't only work over ints and floats, etc. They actually work over all kinds of values entirely, as long as the 2 arguments are the same type. So that's what we're expressing here. They take 2 arguments of type variable type, right? Variable type, but it's the same variable. It's defined down here, right? And they return a Boolean. So for example, you can compare 2 lists, you can compare 2 strings. If you look at the code that I'll post at some point that includes user-defined data types, you can compare those 2. Exactly how it works, you could look at the OCaml manual, which I think specifies exactly how the comparison works. The important thing is that for like integers and floats, it works the way that you'd expect, but it's not possible in the type system that we have to define an operator that only works for ints or floats, but nothing else. You can only define operators that work for exactly one type or operators that work for every type. And so they made the choice to just use comparison operators that work for every type, because often it's useful to be able to compare arbitrary things, for example, for sorting a list. Yeah, so because operators have to work at either only one type or at every type, that's why we have separate operators for integer addition, subtraction, etc., and floating point addition, subtraction, etc. It's because the plus operator needs to either work for every type or only integers. And so it doesn't really make sense to add 2 Booleans. I mean, there's some ways that that might make sense, but there are other types for which addition doesn't make any sense at all. And so addition only works on integers. And so that's why we have this different, integer binary operator type and this floating binary operator type. And so we're going to use these monop and binop signature functions the same way we use the const signature function. And if you look over here on the semantics, you see I just called them signature in both cases, because really that's what they are, right? They're just signatures. Also, the new rules look a little bit scarier. I'll get to that in a second. I did mention that last week. The other thing is there's these 2 convenience functions for constructing list types and function types. I don't know if I actually used the one for constructing list types this week, but I use this function type 1 kind of aggressively. So in this case, we want to make a function type, right? And so the type constructor is the function arrow. You could look at, let's see, we could look at one of these Haskell types up here, right? It's exactly the same. So the type constructor here is this function arrow, and its 2 type arguments are binop and polytype. And so we're just modeling the exact same thing with our PicoML syntax. The type constructor is the function arrow, and the arguments go in the list. And then when we type check those things, if you remember using the decompose rule of the solver, if it tries to unify 2 function arrows, it'll just break them apart and unify their arguments, which is exactly what we want. So, okay, let's go back up to where the rules go. Oh, I went a little bit too far. And okay, we'll start adding things in a second. So first of all, I want to talk about this other syntax. So last week when we did this rule for if, I mentioned that this extra omit premise is kind of a shorthand. And I said that there was at least one rule that I know is not possible to write using that shorthand notation. And so this week I just decided to write them all the long way. The long way is that you augment every typing judgment. So remember, a judgment is a statement that some type environment gamma can demonstrate that some expression has some type. We augment each judgment using the vertical bar with what's called a constraint set. So we use phi for constraint sets. And if you remember how our inference system works, we're already carrying the constraint sets with us everywhere, right? Our monad is keeping track of a list of constraints constantly as we go. And then at the end, we just pull out the list of constraints and solve them. So we don't actually have to worry about all of these union things over here. So like this says, if you want to infer the type of a binary operator, you first have, or sorry, a binary operator expression, you first have to infer the types of the arguments. And then you have to take the union of this new constraint plus all of the constraints generated by the sub-expressions. We don't have to worry about the union part because the monad's doing that for us. So all we have to worry about is omitting this new constraint over here. And that's what this extra omit premise is shorthand for. Unfortunately for the let rule, which looks scary, but we'll get there, don't worry. For the let rule, we do actually need to be able to refer to the constraints, whoops, over here, the constraints phi b that were omitted by inferring the type of this expression. And so I can't write that the short way. But yeah, so over here, again, if you remember what the instantiate function does, it takes a polytype and then generates fresh names for all of the quantified variables and gives you back a monotype. So this says, if we want to infer the type of a monary operator expression, we have to first infer the type of the argument. That'll give us some type tau1. And then our result is going to be a type tau. If you're wondering where tau comes from, good question. And then we want to unify the function type tau1 to tau with a fresh instantiation of the signature for the monary operator. And so where does tau come from? Well, it didn't come from inferring anything else. So really, tau is just a guess. We need to make some guess as to what this type is. And then we need to actually figure out what that type is from the unification constraint. So to make a guess, we're just going to guess that it's a variable. And then if it turns out that it's not a variable, maybe it's an integer or something, we will learn that from the unification constraints when we solve them. So we have a monop x, we have operator m, expression e in environment gamma. Just clean that up. Okay, so what do? Well, we start by getting tau1, which we'll get by inferring the expression. And then it actually, give me a second, I'm not actually looking at my source code for this. I was just going to freehand it, but I should make them match. Okay. And then we're going to get our guess, tau, by making a fresh variable name. So if you remember last week, we talked about this fresh function. It just uses the counter that we have in our monad to generate a variable name that it's never made before. All right. And then we want to get the signature of the monadic operator. So we would start with monop signature m. This gives us a polytype. But remember, we don't want a polytype, we want a monotype. And so we use our instantiate function to get the signature. And now we add our unification constraint. So the constraint is, oops, wait, tau1, yeah. So the function type from tau1 to tau unifies with the signature that we just got. And then the rule says that the final type is tau. Right, over here, we should return tau. Does anyone have any questions about that? If that rule makes sense, then the rest of them should be very easy. No? Okay. So binary operators are very similar. There's just two sub-expressions instead of one. So we're going to, oh, no space. We're going to infer both sub-expressions, tau1, tau2. And again, you can look at the rule on the side and see how this matches. We get our guess for the result. We get our signature for the binary operator, this time using binop signature. And then we omit our unification constraint. And this time the constraint is a little bit bigger, but it's exactly the same idea. Tau2, one type tau. And then that unifies with the signature. And again, we return tau. Why is that complaining? Oh, I missed an equal sign. There we go. Yes. Okay, nice. All right. So that's operators. So already we could start up a REPL and try and type check some operator expressions. Unfortunately, it would still crash because we haven't written the evaluation rules for them. So I think we're just going to do everything in one go and then demonstrate at the end because most of this stuff is pretty fast. So the next rule is the function rule. So we have a name x for an argument in expression e. So let's look at this rule. What does this rule say? This says we need to make some guess, tau1. And again, we have to make a guess because it's not coming from inferring something. We have to make some guess for the type of the argument. And then we insert that binding for the argument and its type into the type environment. And we use that augmented type environment to infer the type of the body, right? That should make sense. You can use the argument of the function in the body. And then the final type will just be the type that we guessed for the argument to the result type, and anything else that we learn about what the type of the argument needs to be from inferring the body will be in the constraints. So for example, if the body of the function is x plus 1, then we'll learn from inferring the type of the body that x needs to be int. And so we carry on those constraints, and so we will learn that the function goes from int to int. So, okay, how do we express this? Well, again, we need to make our guess for the type of the argument. We need to infer the type of the body, so infer e, but we need to do it in an augmented environment. So we use insert env, and then this is slightly wrong, but I'll explain why and fix it in a second. And then we return function type from tau1 to tau2. So, okay, this is going to complain now. The problem here is that our type environments are supposed to have polytypes in them, but tau1 is a monotype. And so actually, if you saw that type error there, that's exactly what it says. It says can't match type polytype with monotype. So in order to fix that, we just have to recognize that a monotype is just a polytype that has no quantified variables, right? It's a polytype where in order to make in a fresh instance, you should do nothing, right? You should just use the exact same type that you were using before. So all we do is we wrap it up in a for all with an empty quantified variable list. And now this does exactly what we want. Note that that's different from generalizing tau1. So last week we talked about the function called generalize, which finds all of the free variables of a monotype and quantifies them. We're very explicitly quantifying none of them, as opposed to quantifying all of them. We will use generalize later. You can see it in the let rule. So okay, next rule, appexp. So we have a function f and an argument e. What does the rule say we should do? It says we should infer the type of f, infer the type of e, make some guess for the return type of f, and then emit the appropriate unification. So let's do that. So, oops, there we go. So we'll get tau1 from inferring f, we'll get tau2 from inferring e, we'll get tau3 by making a guess, and then we unify the function from tau1 to tau2, or sorry, to tau function from tau2, that's the type of the argument, to tau3, the return type of the function, and we unify that with tau1, which is the type that we inferred for the function, right? So we inferred tau1 as the type of the function, but we also know that the type of the function should be function from the type of the argument to the guessed return type. So we unify those. And then we return tau3. And so again, that's just coming straight out of the rule. Hopefully the rule makes sense, but the rule is hopefully more enlightening than the code, right? The code is just an implementation of the rule. All right, so now we get to an expression that's really interesting, or to a rule that's really interesting. So I think first I should maybe show the incorrect implementation and then explain what goes wrong. So if we just ignore this big rule on the side, really what we want to do is very similar to the function expression, right? What we really want to do is we want to infer the type of the binding. So let's say like this. And then we just want to infer the type of the body and return the same result as the type of the body. But we want to do it in the augmented environment, similarly to what we did above, like this, I think. Is that type check? Come on. Yeah, okay. So this looks very similar to the function expression rule. And so you might, in an ideal world, this would work, right? This is really simple. We really wish that this would work. The problem is that in our type system, we want to have something called let polymorphism or let generalization, which means if I write, for example, let id equal fun x to x like this, I would very much like it if this identity function was not constrained to a single type, right? I would like it so that if I use this identity function at the type integer, it won't stop me from using it with Booleans later, because it should work for both. And so the problem is, once we have the type of id, we have to generalize it. Okay, so you might say, how come we have to also do this solve thing? Why can't we just generalize the type? Well, the problem is because we don't solve constraints until we're all the way done with inferencing. If we generalize immediately, we might generalize away a variable that was supposed to be solved. So the shortest example I know of this is lambda function, which takes x, goes to let y equal x plus 1 in y. And what happens here, if you just generalize the whole thing, is you'll get a constraint that x should be int, which also gives you a constraint that the type of y, which we guess is a type variable, we get a constraint that says that type variable should also be int. But then we generalize that type variable, and then we instantiate it again in the body. And there's no constraint that says the instantiated one needs to be int, because the constraint uses the name of the one that we generalized. And so we'll end up giving this function a bogus type. We'll end up saying that it has type tick a to int. Whoops, what did I do? Sorry, okay, has type tick a to int. And if you remember from last week, type variable names just start with a tick by convention. This is obviously bogus, right? The argument needs to be an integer. So in order to deal with that, we have to actually solve the constraints that we omit from inferring the body first. And so what we do is we use this function called listen. And I'm not sure if it will give me the type here. Yeah, that's not right. Come on. Yeah, oh, that's hard to read. Okay. Well, basically what it does is it augments the return type of infer with the list of constraints that it emitted. And so we get that, and we name it phi. And then the rule says we have to solve that to get a substitution. So we will solve phi. There's one other problem here, which is that solve, as you can see, returns either instead of our infer monad. The library gives us a nice function for dealing with that called lift either. And so this just makes the problem go away. We can use functions that return either as though they return things of type infer. And then we're going to generalize. So we're going to apply the substitution to tau and generalize it. We'll call that tau b. So we're going to generalize in the environment gamma the result of applying the substitution to tau b. And if you need a refresher on all of these helper functions, you can look at the talk from last week. I think I don't have time to go over all of them again. Really looks like I don't. And then over here, instead of using this tau b, or yeah, instead of using that tau b, we're going to use the generalized one. And then this solves the problem. So that type error will go away in a second. Okay, so in the interest of time, I just need to move on. But yeah, hopefully you can see how that's just, again, an implementation of the rule. Again, this rule looks scary because there's a lot of stuff going on, but we can break it down into pieces, do it step by step. And you'll see it really looks very similar to the last rule. It's just a little bit bigger. Ooh, whoops. So first we need to make a couple of guesses. And then just for convenience, we'll define the type of f to be tau1 to tau2. We need to infer the type of the body and get the constraints. So we use listen again. And then we're going to have a pretty big augment to the environment, so I'll put it on a new line. Here we don't want to generalize things because these aren't the let bound things. These are just the types of X and F that are available in the body because it's recursive. So we insert X, we insert F, tau F to gamma. We do our inference there. Then again, we need to solve the substitution, or sorry, we need to solve the constraints to get a substitution. Solve phi. However, you'll notice in the rule here, the solve, we don't need to only solve phi. There's also an extra constraint that we have to solve. And I would encourage you to look at the rule when we're done and try and figure out why this extra constraint is needed. What problem does this solve? Or maybe you could even download the code and remove it and try and figure out what goes wrong. And then, whoops, we infer the type of the body in an augmented environment again, but this time we want to augment it with F's type and we want to generalize it. So we do the same thing we did above, tau F, gamma. All those errors should go away. Come on, yeah, okay. So these are all of the typing rules. Hopefully it's clear exactly what was going on here. I don't have, or I don't want to spend the next 15 minutes just talking about this. So hopefully this is clear. If anybody has any questions, feel free to ask in Slack. So, okay. The last thing to do is add the new evaluations. And as you can see, these are all much simpler, so this should go by very fast. There's one thing that I want to point out that I think I didn't point out earlier, which is that there's a new type of value. So we have closure values. If you guys remember from the simply typed lambda calculus lecture, we had closures to remember the environment that functions were defined in. We need to do the exact same thing. These should look super similar. I think it might actually be identical. I'm not sure. Oops, not far enough. Okay. Oh, still not far enough. Yeah, there we go. Okay. So if we come all the way down here, we can just start implementing these rules pretty quickly. They're very straightforward. The only other thing is there's these really big helper functions that I left predefined. What they do is they take a monadic operator or a binary operator respectively, and they just turn it into the corresponding function on values. So lift monop takes a monop and produces a function from one value to a result value. Lift binop takes a binary operator, gives you the corresponding function from two values to a result value. If it's unclear, I'd encourage you to think about why there's so many missing patterns. So like, why does int plus op not have a pattern for float vals, for example? The program will never crash because of that. And if it's not clear why, I would encourage you to think about that. So anyway, monop expressions, again, wait, whoops, I need my source code. Yeah, here we go. Okay. So what does the rule say we should do? It says we should, it says we should evaluate E in the environment, right? So first thing you need to do to evaluate this is evaluate E. And then what result do we return? Well, we just lift the monadic operator on the result. So lift monop M on the result. That's the whole rule. Similarly, for binary operators, there's just going to be, two sub-expressions instead of one. So how do we want to write this? I'm just, in the interest of time, I'm just going to do it this way. So we evaluate E1, we evaluate E2, and then we lift the binary operator on the results. For short circuiting, if our language had side effects, we would want to be careful here, and we would want to have a special case for if B is and op or op. In the source code that I pushed to the repository earlier today, I actually did have special cases for them in order to implement the short circuiting explicitly. In the interest of time, I'm not going to do that right now because it, as I've been saying, it doesn't make a difference. But you can check out that if you want to see how it works. It's very straightforward. So the next rule is function expressions, and they don't really do anything interesting, right? To evaluate a function expression, all you do is create a closure. What's in the closure? It's the name of the argument, the body, and the current environment. So very straightforward. And then we get our application expressions. Okay, so what does the rule for applications say? It says the first thing you need to do is evaluate f, and it says the result should be this weird thing with the angle brackets. So this is the formal notation for a closure with the angle brackets. So this says our result is going to be a cloval with some contents. And that's the result of evaluating f. And then we also need to evaluate the argument in the same environment. And then the final result is just the result of evaluating the body after augmenting the closures environment, env, with this binding for x. So again, just very straightforward implementation of the rule. Another thing here is, again, notice that we're not doing pattern matching to make sure that this is a closure value. We're just assuming that it's a closure value. And so again, if it's not immediately clear why it's safe to do that, you should think about that. Okay, so let expressions. This rule should look very similar to app expression because lets are very similar to applications. The difference is we just don't have that intermediate closure. So we just evaluate the body, and then we evaluate the expression in the let after. Wait, did I do something wrong? Yeah, that should have been x. After inserting this binding for x. And then let rec in expression is very interesting. So I mentioned when we started in the intro video that in a strict language, in order to evaluate let expressions like this, you have to do something like really annoying, right? You have to have some special value type for recursive values. And then like while you're evaluating it, you have to like pick it apart repeatedly and treat it differently from all other kinds of values. And it's really weird and it's really annoying. Because Haskell is lazy, we don't have to deal with any of that. So what we're going to do is we're going to we're going to create a special closure that is mutually recursive with a new environment. So it has a reference to itself. And so how do we do that? We want a closure with argument x and body b. And this is the closure for f, in case that's not clear. And we want the environment to, well, actually, let's just use env prime. We want the environment to be env prime. What is env prime? Well, it's env, but with an inserted binding for f that binds it to clo. And so you can see here, what we end up with is we end up with a new environment that has a binding from f to clo. And what is clo? It's a closure value that has a reference to the same new environment. So it has this self-referential pointer in it. This kind of thing is very hard to construct in a strict functional language. It's possible, but it's really annoying. But because Haskell is lazy, it's no problem at all. We just write this, and it seems like it should cause an infinite loop, but instead, just like magic, it works. And then what do? We evaluate E in env prime. And so that's the whole rule. There is one other thing that we could talk about, but instead I want to just go straight to demonstrating. So there's this new rule for let rec statements. I just left that implemented, so I think it's in place down here. If you want to look over this, you can, but really it's very similar to what we just did. It just constructs the closure value and the new sigma, and then does the same thing. The interesting thing is that instead of using some complicated type checking rule, it just type checks an equivalent let rec expression. So that's a nice little shortcut. So okay, that's all the code. So let's see. Let's go over here and load it up. And so now we can start doing some interesting things. Whereas before the language had no features, now it can really do stuff. So like, for example, we can type check a function like this. And you can't really print anything for a function value, so we just print closure. But this is the type that you would expect, right? It doesn't care about its argument, and it returns an int. We can type check, random expressions like this. We can use it like a calculator. Note that it gets the precedence right. So 2 times 3 binds tighter. We can try that expression that I was talking about earlier, equal x plus 1 in y. And notice it's not bogus, right? We know that the argument type has to be int. We can even, try evaluating some applications. So for example, equals x plus 1 applied to 5. Writing things like this is pretty annoying. So we could give it a name. So this is the increment function. And we could write inc5 and inc10, use it like a calculator like this. We can also do some interesting things like recursive functions. So I could say, or I could define factorial. What is the factorial? If n is less than 1, actually let's use less than or equal to 1, then it's 1. Otherwise, it's n times the factorial of n minus 1. And so we could even, compute some factorials, and you could check for yourself that these are the correct values. And so now we have a real language that can do interesting things. We can semicolons. We can make lists. Manipulating lists is hard because our language has no support for taking them apart. But we can put them together. We can also, try and write a list that shouldn't type check, and we'll get an error, right? Lists need to contain things of the same type. If you want to play with this, you can just grab the source code off GitHub, load it up into the interpreter, do the same thing I did, :main. And you can just try entering all sorts of expressions, including some things that shouldn't type check. One interesting one, if you're familiar with lambda calculus, is called the omega combinator. This doesn't type check. And if you tried to write this in Haskell, I think you would even get the same type error. I think this would maybe be D instead of C, but the rest of the error should be exactly the same. And so what's the problem? The problem is that, well, X needs to be, like the type of X, which is a function type, needs to be the same type as its own argument, and that leads to problems, right? The type of X, tick A, needs to be the same type as its argument. The only way to solve this unification constraint is if the type of X were infinite, right? If it was function from tick A to function from tick A to function from tick A, et cetera, it would never be able to return. And so we just disallow that because we're not interested in things that are guaranteed to cause infinite loops. And so in that way, type systems can help prevent some classes of errors that are normally very hard for programming languages to prevent for you, in addition to just silly type errors. We also have our floating point addition, so we can do things like this. We get floating point math. We have string concatenation. Oops, go away highlighting. So I can say hello concatenated with, I don't know, a space concatenated with world. Ta-da. And so again, like I said, this is the string concatenation operator, which is a weird symbol for it, but not my choice. And so yeah, now we have a real programming language that you could use to do some semi-interesting calculations. I mean, you could really use it to do any kind of calculation. It's just very hard without user-defined types to do meaningful things. And so I'll post a version of the code that supports user-defined types, and you can look around with that and mess with it if you want. But there's just way too much to do to support user-defined types, I think, for us to do it here. Like I could spend easily a whole month talking about all the complications that arise with pattern matching and type name coherence and stuff like that. If you're still interested in implementing interpreters, you could find a lot of literature about those things really easily. I think the people that write papers about stuff like that are very approachable. I think their writing style is very easy to read if you've never done that kind of stuff before, because I read those papers when I had still never done this kind of stuff before. And you could even use this as a base implementation to try and implement those things on top of if you don't want to use my implementation. So yeah, I think I'll talk to Reed about what we're going to do in the future. Our idea was to let you guys like pick some projects to work on together in the kind of PL space. Like maybe you want to work more on this interpreter. Maybe you want to work on an existing open source interpreter or start your own. All of those things would be okay. Reed's not here this week, obviously. I think he'll be back next week, but I'm not sure. But yeah, I'll talk to him and figure out what we're going to be doing. But it's 4 o'clock, so if you guys want to go, feel free. If anybody has any questions, you can ask them now. I can stay for a while. Otherwise, thanks for coming.
Thanks.
Right, thank you.
Okay. So